A very good afternoon to the organizers, the chairs, and one and all present here. I'm Arun Shivasubramanian and my colleagues Sheel, Akash, Ridhya, and Bharti Ganesh. We all are AI practitioners at the Resilience Business Grids LLP. We are here to present our work on performing text segmentation to improve optical character recognition on multi-scene text. The agenda for today is as follows. We'll be starting with the abstract of our work, followed by the introduction to the main problem statement. We'll be discussing the related works done in this realm and the research gaps we found through literature review. We'll be explaining the proposed methodology by which we tackle this problem, and we'll also be discussing the results which we have obtained from these. A detailed comparative analysis of the state-of-the-art algorithms which have been tried as a part of this work will be summarized, and we'll also be concluding our work and presenting the future directions in which the research community can proceed with this. Optical character recognition, or OCR, is a revolutionary technique that aids machines in retrieving textual content from images to perform further analysis. However, OCR has its own limitations, especially when dealing with degraded or low quality images, which can actually impact the overall reliability of the text recognition process. Thus, the system's accuracy is usually contingent upon the quality of the input image. Now, efforts to modify the text detection and text recognition modules in existing OCRs fail to work completely in complex dynamic environments due to the complexity of the background information of the input data. Thus, a new first of its kind annotated dataset called OCR-SBT for digital text segmentation is proposed in this work, along with a novel pre-processing pipeline that leverages deep learning to perform text retrieval for complex backgrounds using binary semantic segmentation. Now, this work will help the research community to improve OCRs for several real-world applications by alleviating the problems related to background contextual information and completely obfuscating the text recognition module. OCR is an essential natural language understanding tool to digitalize vast volumes of text from numerous sources for several downstream applications. However, its accuracy limitations with challenging input necessitate continuous improvements for information retrieval from low-level language resources. So OCR has difficulty reading printing text with uneven typefaces, smudges, and poor contrast, and mistakes that could often change the meaning of the text. It is even more difficult with handwriting material, as it varies so much in style and readability, and with less prevalent languages and scripts that don't use typographical tools. Although several works have been proposed in the literature to improve the image quality and make the model more robust for character identification, they usually fail because they cannot accurately handle multi-contextual background to perform scene text recognition. Now, deep learning approaches have become very popular for performing several computer vision tasks. However, there's no focus on creating a DL model for segmenting text pixels in fonts of multiple classes, sizes, and orientations in multiple background conditions. Now, this necessitates a pipeline that efficiently determines the characters in the foreground and the complex background, and a systematic annotated dataset, which is the OCR-SBT, or optical character recognition with scene binarized text, to train a robust model for multi-scene digital text recognition is performed using state-of-the-art architectures in this work. Talking about the related works in the literature, Vibhava Kondrov and Daisy Try use techniques such as Otsu thresholding binarization. However, the binarization techniques did not assist the OCR in retrieving accurate textual information compared to the OCR on the raw image data itself. Young et al. Proposed an effective edge descriptor for OCR termed as Improved Local Binary Patterns, or ILBP, that searches across scale space to address the noise issues and making it more robust. Akhtar Zainab et al. Proposed a PLS, or partial least-square based approach for character recognition on a newly proposed CARS 74K dataset to benchmark character accuracy of 99%. The morphological analyzers are also readily available lexical resources, and Nitin et al. Performed contrast enhancement of the unclear spaces as a pre-processing measure before OCR is performed. There are several other traditional techniques in literature, and some of them do have promising results. However, better techniques to improve quality and high precision OCR techniques have emerged in the literature, and they can be used in combination with the trends in deep learning. There have been several improvements in the DL community to improve OCRs. Krishnamurthy et al. Developed a novel CNN architecture to improve handwritten character recognition and validated the performance in NS data. But it is found to fail on real-time data and in cases with multi-contextual backgrounds where the text recognition itself fails. Muttureka et al. Fine-tuned the Inception v3 architecture to perform character recognition from noisy newspaper information with the assistance of pre- and post-processing measures. However, it is a computationally complex measure compared to the approach suggested in our work. With the advent of transformer-based networks for OCR such as TR-OCR and the recently introduced DocTR and Paddle OCR, there have been a lot of progress, but the text recognition module must perform text retrieval amidst complex background conditions, fonts, and font sizes. So the primary gap in literature is a dire need to pre-process text present in low-quality documents before performing OCR. Computationally efficient methods to avoid text recognition modules can be incorporated. To the best of our knowledge, There is no work on accurately segmenting handwritten and digital words in a Word document in different styles, fonts, sizes, and orientations without removing complex background information which is necessary for accurate detection. Thus, we leverage a text retrieval using binary semantic segmentation of every character present in the image using deep learning architectures UNet and UNet 3+. Our study relies on the input images of the synthetic image collection, where the original curators had added various text effects to the images, such as geometrical distortions, alignment, cropping, fitting related issues, etc. We chose a subset of 1684 text images that reflects a cross-section of the sizable dataset. Now to get the segmentation mask, we use binarization performed using color k-means clustering with two clusters, one for the foreground text and one for the background. Now once we obtain the images and the segmentation mask, they need to be resized to pass to UNet and UNet 3+ for semantic segmentation of characters. UNet is the benchmark backbone for several segmentation tasks, and UNet 3+ is the improvised version of it with multiple skip connections between the encoder and decoder blocks. The pre-trained OCRs are then leveraged to find the actual word. Now we did ablation experiments using image enhancement approaches such as extra super resolution or ESR GAN and stable diffusion 4x to determine if super resolution improves the results like we observed in some of our previous projects. All the experiments of this task were done on the Amazon G4 large EC2 instance that leverages a Tesla T4 GPU with 32 GB RAM and 16 GB VRAM. 6 experiments were conducted using a permutation of two architectures and two super resolution techniques to determine the model that yields the best evaluation metrics. The metrics support the qualitative results as the text areas are extracted accurately with minimum distortions. As theoretically expected, the performance of UNet 3+ is better than UNet because of the multi-level skip connections which help the model to learn the foreground information as well as the attention mechanism which helps the model to capture the global and the local features more accurately. It is also evident that increasing the image quality using super resolution techniques like label diffusion will help the model to predict the characters better than the raw images. However, in case of SR using ESR GAN, the results are only comparable to the ones in the raw image, suggesting that the GAN is not the optimal solution to generalize the distortion of textual information. Although the results of stable diffusion are better than the other experiments, one must consider the time complexity, where stable diffusion is 10x lower than ESR GAN, while consider the applications for which the task needs to be deployed. The model's performance is also evaluated on real-world test images outside the synthetic dataset by considering samples with text with patterns, Gaussian noise, and blur. Now, the model could detect appropriate text in various data samples that resemble the test data, and in most later cases, the OCR engine also performs better on the binarized image better than the original image. However, the model did generate some false positives in a few cases by not being able to eliminate the background information. Nevertheless, the model makes accurate foreground separation without which the OCR engine fails to predict the output text accurately. In a few cases with multi-text and text with Gaussian noise, which are not even a part of the training corpus, there are just a few false negative cases with areas of the characters being removed from the annotation, thus necessitating the inclusion of a few more samples of each case in the proposed dataset for robustness. Even in extreme cases such as handwritten text, the model never fails to recognize a handwritten or a digital character in such a scene, as the inaccurate removal of vertical lines is treated as a punctuation, but all the characters are easily detected. However, it is only trained on digital text, and thus the performance can further be improved by fine-tuning an OCR trained on such binary segmentation maps alone to get improved text in the future. Two failure cases must be addressed. Firstly, the model fails to binarize multi-text in images captured with complex backgrounds. This is because the background context did not vary within the image itself. Also, no images in the training corpus contained multiple words in a single image. Thus, only the most prominent word present in the image was detected, and as seen in the second example, the model also fails to identify the textual content taken from a distance much larger than the expected due to the training data not having such samples. However, in such cases, it is possible to get the required output if we just crop the particular region and make the data resemble the testing corpus for accurate predictions. We conclude this work, which utilizes the progress of color k-means clustering to create annotations of multi-scene text to enhance the results of OCR and completely eliminating the problems related to background contextual information. The proposed approach was tested on the validation dataset as well as real-world samples to give good qualitative and quantitative matrices and can be directly used for obfuscating the text recognition module for several real-world applications on a large scale. Future works can include extensions of this work by creating a dataset containing the handwritten data as binary segmentation map. Now, the study can also be extended to resource-poor languages of Asia and Africa, and the applications of the same can be extended to works related to context drift. There are also some cases where this model fails, but since this work is very promising, the training corpus can be improved to address the limitations of the study. These are the works analyzed as a part of the literature survey to identify the research gaps. We thank you all for your patient listening.